Hello and welcome. Thank you so much for joining me. This is part two of It's Dry, It's the Flood. I have edited down the Young Earth video to take out some of the rambling and taking out some of the places where he's repeating the same point over and over. I kept enough of it where you can see what he's talking about. And if you want the entire context, a link to the entire video will be in the description. So with that, welcome back, Steve, and thank you so much for helping me with this one.
Sure, no problem. I assume you took all the probablys out. That probably
These are some of the ways we figure out that the continents were greatly eroded. These erosional products are not found nearby as if it was eroded by uniformitarian time over millions of years. They're gone. They're taken totally off the continents. This is what we expect in the flood. I mean, if we had millions of years of erosion and soil formation, we should see dozens of feet of thickness of pulverized rocks, soils, or even hundreds of feet.
really wish you
There's
would
exceptions
stop
because
we
have a
crap.
Yeah.
Soil doesn't take millions of years to form, at least not topsoil.
Oh, really? Okay.
Yeah, take a few thousand. We have interglacial topsoils in the glacial stuff, and that's how we define some of the episodes, if you will.
Mhm.
Between one advance and one retreat is there's enough time for soil to develop, so it doesn't take a long time if you have the vegetation to do it. You know what else can cause erosion to look like that?
What's
Time.
that?
Lots
Oh,
of
time.
and uplift. There's no mystery here, and I noticed that when I sat through the whole thing
Mhm.
after our first meeting. There's a lot of stuff he tries to make sound like a big deal, but it isn't.
Mhm.
Not a thing. Time and tectonics will do the same thing. There's no need to come up with some hypothetical flood, which he admitted you needed a miracle to happen earlier in the video. So
a lot of post-flood landsliding and other features that would form thicker debris piles or rock piles and soils. This erosion we know happened rapidly. And the best example on this is Devil's Tower. Now, Devil's Tower in northeast Wyoming is approximately 1,200 feet tall and 1,000 feet wide. It goes straight up. It's very likely the throat of a volcano.
I've been to Devil's Tower many, many times. And as a
Mhm.
geologist, we have to do a 6-week. You can either do it in your undergraduate or before your graduate. It's called field camp, and it's 6 weeks long. Devil's Tower is one of the places you go, and we have to map that area. And since then, I've been there many times. I actually was given some rock by somebody who had permission to take it from there, and I've looked at it in detail myself. So if he mistalks about the rock type, you're going to see my eye twitch. And just so you know, I know a lot of people call it basalt because it has this thing called columnar jointing. Columnar jointing can happen in sandstone. If you don't believe me, Google sandstone South America, columnar jointing.
Okay, what
But
is columnar jointing?
columnar jointing is a type of joint, a break in the rock. It's that
Oh,
the
okay.
columns. And it
Mhm.
usually does form in basalt. So people assume anything with it's a basalt. But that rock has no quartz in it, no free quartz. So it's actually what we call phonolite or tephrite. So yeah, so it's totally different. It's a totally different side of the chart we plot these things on. But anyway, it is still a fine-grained igneous rock. And as for the volcanic neck thing, that's kind of a hypothesis we know didn't happen. The problem with understanding Devil's Tower is columnar jointing. Well, not always, but usually forms perpendicular to the way the lava moved, or so if it moved laterally, your columnar jointing is straight up. If it moved vertically, it should be this way. Well, Devil's Tower is this way. So it kind of is a conundrum, but some people think it's what's called a marred diatreme, which is like a surface flood happens to be preserved, because if you look at the columnar jointing, eventually it goes down and lays out.
Mhm.
So it changes direction to the vertical underground, which is where it should be. Sorry, there's no tree roots. Hate to disappoint everyone. It's probably the blob where the marred diatreme came up on the surface. That's the best working hypothesis we have.
But Devil's Tower was likely formed in some kind of a local flood there?
No. When I say flood, I mean lava flood.
Oh,
Flood
okay.
basalt, a flood. Since it's not a basalt, I didn't want to say basalt. It's a flood as in a lava flood. And you know me, I hate the terms lava and magma. I use the term melt because, you know, it's annoying to differentiate, because this is right on that cusp. Well, is it a magma? Was it a magma or a lava? You know, so it's obnoxious.
Some other mechanism still has to form under sedimentary rocks. So the sedimentary rocks in northeast Wyoming, in that whole area there, had to be at least to the top of Devil's Tower, and very likely much deeper, maybe 6,000 feet above that. In fact, the uniformitarian geologists believe it was 6,000 feet deep there. But as you eroded all this sedimentary rocks from the top of Devil's Tower, 1,200 feet down, Devil's Tower was hardly eroded at all. The width of it's still the same, and supposedly this happened over millions of years. How can you erode a horizontal surface over thousands of square miles, and yet Devil's Tower with vertical walls is hardly touched at all?
That's easy. Devil's Tower, everyone draws on that because it looks real cool, but there's similar lava deposits of phonolite and tephrite all around that area. They just don't look cool. They're just mounds. So anyway, the sediments that surround that are Mesozoic mostly. I think there might be Triassic spearfish formation, and I'm trying to remember from 23 years ago here. So, and all those, since they were deposited in a seaway, the Greenhorn Seaway, and then after the Mesozoic, the entire that side of the continent started to get lifted up because we were going to have the Laramide orogeny. We're going to have those mountain building event. So this whole thing's getting lifted up, and that didn't have time to lithify. So what was ever there just started eroding. And Devil's Tower, being not only an igneous, lithified, hard rock compared to everything else around it, and you still see the deep valleys and everything around that. It's not this perfect plain that, you know, he likes to talk about. It stayed there. And plus, it's complex geology. The fact that jointing changes direction like that just added to the structural integrity of this thing. So as you notice, that the columnar jointing that was probably much more extensive, that's all gone because you didn't have that neck. It's not a volcanic neck, but that area like you have at Devil's Tower. So it's nothing complex. There's nothing mystical about it. It's an easy explanation.
One thing that he said in that segment that I'm wondering about is he said at one time Devil's Tower was covered by 6,000 feet of rock, and all of that rock eroded off, and that you can see the remnants of that erosion in the area around Devil's Tower. Is he right about that, or was there a lot of rock on top of it and then it lifted up and then
No,
it okay.
Devil's Tower is young, but it's sometime in the tertiary. I forget exactly where, or Paleogene, whatever you want to call it now. We has to do with the naming of periods. We got rid of tertiary in 2012, then we decided to bring it back on this side of the pond. Everyone else got rid of it, but us. The sediments around there are mostly Mesozoic, quiet seaway, no volcanics at all. And that got uplifted before the volcanics and erosion did start. Whether it was 6,000 feet, that's an assumption, and you can roughly calculate that, but it could have been 0 feet. You know, it's not one of the things like you could be 6,000 feet plus or minus 30 feet. It's 6,000 feet plus or minus 6,000 feet. You know, it's one of, and if Devil's Tower is a Mar diatreme, there was erosion going on long before it formed because it had to be formed near the surface or at the surface. So when it erupted during the orogeny that built the Rockies, it would have been near the surface to begin with. So you had a bunch of rock, then eroded, then this happened and eroded some more. That you don't need a flood. How's a flood going to preserve that? It makes no sense. And that doesn't surprise me. Young Earth creation is nothing surprising there.
Just in front of us is Hart Mountain, which is one of those limestone blocks that broke off from a huge limestone depositional area east of Yellowstone Park and slid, moving over 100 miles an hour to the southeast. So after all this material collected in the valley, the top was eroded, about approximately 2,000 feet or more, and I believe that happened during the channelized phase of the flood.
My mentor, professor, partner in crime, Dr. Malone, actually, and his kids, which also decided to become geologists. Can't believe they're adults now. Anyway, they worked this out, Heart Mountain. They think they got it. I've read the papers. There's nothing I can do to falsify it. It looks solid. By the way, there's diamonds near the bottom. This is the diamond debris, I should say. This is what we call like the Lewis thrust. It was over-thrusted upon younger rock, which happens in orogenies. But what happened then is this section detached and moved away. I don't think it's 100 miles. It's called a detachment block. We see this a lot. And we even see it back as far back as, in the Paleozoic as well. There's one in the Upper Peninsula that might actually be it. All the old timers think it's a volcanic neck, but it's not. It can't be. It's got to be a detachment block. Anyway, detachment blocks happen. Where's the one? There's one actively moving right now. Heart Mountain is what we call a detachment block. They're usually associated with rifts. So there's a lot of them in the mid-Atlantic rift and stuff like that, but they also happen in failed rifts as well. We have, there's some that are still active today in the Basin and Range province, where we have active extension going on, and North America may or may not split there. Now, these things can move and slide laterally down slope. If you're down slope in a subsiding basin that's, faulting, say this is your block, it can detach and slide along. And Heart Mountain seems to be one of those blocks. It's old, but it's one of those blocks. I think maybe 50 million years ago this started, when the whole mountains ranges in the area, when all this volcanic stuff was happening, when the extension was happening due to uplift. You get stuff like this even on the continents. And like I said, in the Basin and Range, it's happening today. You do get detachment blocks that are still moving, not to this scale, because it's in the rift is just forming. When the very early stages of a rift. Will it stop? I don't know. Will it continue and split North America? I don't know. I think it will, but I don't know for sure. So these things, they can either move slowly, as time goes on. Friction, this is physics. If it starts to detach and the ground beneath has high enough friction, that block isn't going to move quickly. But if there's not a lot of friction, it can become like a landslide and shoot out. So Heart Mountain didn't travel 100 miles, I don't think. I think that's exaggeration.
Well, he said it traveled 100 miles an hour.
Oh, 100 miles an hour?
Yeah, that's what I was going to ask you about.
We think it did happen quickly.
Okay.
It's more of a landslide scenario, little friction, and it went. And that's why you get heated material at the fault contact. That's because the whole generating of heat thing. And it probably moved after that too. So, but just not to that extent. It's only going to go can. So 100 miles an hour?
Rock slides could move that fast, so couldn't they? Yeah.
Oh, yeah. Rock slides can move that fast and faster. So it's not unheard of.
It's not yeah.
The granite crust was level midway in the flood, about day 150, and parts of the granite went up and parts went down. The total differential vertical tectonics is up to 45,000 feet, based on the height of the Wind River Mountains, the highest mountains in Wyoming, which are up to 14,000 feet, and the deepest part of the granite, which is in the Hanna Basin in south central Wyoming, which is 31,000 feet below sea level.
Go ahead.
I mean, this is all due to the building of the Rocky Mountains, the Basin and Range extension, the Colorado uplift. It's tectonics. There's nothing special about this. His numbers, I don't know how he knows that, because in order to know that, you would have to drill down into the granite. I mean, you can tell where these things are through seismology, But in order to confirm that, you would have to drill down into that granite, do mineral analysis on the distinct layer, and go look for it uphill. That and you can get the the movement of the fault, assuming it's vertical.
Mm-hmm.
And most of these aren't. And he's got a very up and down concept of tectonics. Instead of plates sliding, the recent video I did about that lady who misunderstands plate tectonics to the nth degree has the same concept in her head. And it's just without the flood. It's a little harder in thin skin deformation thrusting, because thrust faults are just really low angle reverse faults. It's a special name we give them. That's all they are. So to give an exact number like that, he can't really do. But you can, through seismology, get the depth of that granite, because plus that granite was probably eroded first before the sediments were put down. So there's no way to determine that. You can determine that with like sedimentary rocks easier, because you can correlate those on the fault. If you drill down a little, you can correlate that. If it's a nice vertical normal fault or reverse fault, if you see that sandstone layer in a cliff here, and then you drill down and it's here, you can subtract that. And generally no. But for attachment blocks, these thrust faults, all this stuff, you really can't determine that unless you have marker beds that are well known and well defined, with well defined thicknesses. And massive batholiths don't have these things, which usually most granites are. They form deep underground, so they're blobular, for lack of a better word, and they cool underground. So they don't have that nice layering usually. So there's no way to determine, thickness of that, or how much is thrown up and something, especially when your up top has nothing on it, has no sediments to sit there and try to correlate.
When he was talking about the San Rael swell, he was saying that he calculated the erosion depth. And I went and tried to research calculations of the erosion depth of that swell to see if his figures agreed with what other people in the field were saying. And I couldn't find any figures at all. Not his, not anyone else's either.
It doesn't surprise me.
Okay.
Because he is saying his calculations, but he's not showing any of those calculations.
Right, exactly. I wanted to check his calculations and I can't find them anywhere.
And that is the scientific method in action. If you can't falsify it, you shelve it. You can ignore it. That's the beauty of science that you don't have in a lot of philosophy. If I can't test it, maybe in the future it'll be testable. Maybe someone will do the work. But for right now, I can't. I can ignore it. It's got this filter that philosophy doesn't have. I don't have to entertain every idea because some guy sat there and said, my calculations show them. Is there something like we don't usually worry about that? The last video you showed the continuation of the lines. Like I said, usually that lateral continuity is for smaller areas and to understand local anticlines and synclines and things like that. Because like sedimentary rates in geology, we don't really try to figure that out anymore because it doesn't mean we have all these zircon dates now. And, it makes sense. You get a sandstone coming in slowly, and then all of a sudden you get a sheet wash flow and you get a foot deposited like that. We don't worry about it any more than we worry about, sedimentary rates. We don't worry about erosion rates on something that eroded millions and millions of years ago. We just don't worry about it because it's not something that's really calculable. I mean, you can only do lateral continuity if you have the sediments on both sides or the rock layers on both sides. You can't just sit there and extrapolate what happens in Grand Canyon in Alaska. You can't do that. And that's the kind of stuff they try to do. Even that diagram you showed last time, that guy only took it to a certain part before he knew he couldn't take it anymore, and he stopped drawing the lines. Because he knew after that, it was not practical. It's probably faults there or something like that. Structural geology gets in the way of their flood all the time. That's why they never mention it. And for those of you that don't know, structural geology is more like engineering. We use a lot of tools. We use stereo nets, Moore circles, all that stuff, stress versus strain, it's all that stuff is structural geology. We're just applying it to the natural world, and it works. So, because, it doesn't matter if I'm breaking a cylinder in a lab or the rock is in situ, and I'm trying to work that out because the laws of physics apply to that in situ rock as much as they do to my concrete cylinder. Those laws don't change. So that's what structural geology is, and you'll never hear young Earth creationists talk about it. Well, number one, because it's really complex, and I don't think most of them can do the math. You know, a lot of trigonometry and stuff involved, but you can also solve these things graphically too. It's faster to do it graphically, and that's how I do it. That's how I passed the professional geologist test back in 2011. Is I didn't run one calculation. I did it manually. So just faster. It's faster to do it manually than it is to fool around on a calculator. That's someone there. You know, I see you. I think it's Hawk. It's probably Hawk.
Filled in with sediments up to about 7,000 feet above sea level. So there's 38,000 feet of sediments in the Hanna Basin.
So the water is pouring into the earth, bringing sediment with it. The sediment seals the rift and fills the valley. Is that possible? Shouldn't we see huge sediment columns beneath the surface? And are there such? We're in the receding phase. And since the water is having to leave the surface of the earth and go back into the deeps, from whence it came, and if that were really the case, that there were these fountains of the deep that exploded outward, and then now in a receding phase, the water is pouring back into the earth, bringing sediment with it, which is sealing the rift into which the water is pouring. First of all, is that even possible? Then if that had happened, shouldn't we, when we excavate, find huge columns of sediment that are below the surface?
I think I see what you're asking. You're basically asking that during this flood moving out, it would still be carrying sediments with it, and it would deposit into these valleys. It's also cutting down, right? Supposedly. Okay. Yeah. You would. I mean, you would see completely different deposits than we see. And in his model, the flood happened after all this rock was deposited. So it's not like most young Earth creationists. So notice I'm not trying to explain any of these rock layers like the young Earth creationists do. The strata, he's not going, because his flood didn't happen at the Precambrian-Cambrian boundary. His happened, at the modern land surface or close to it. His hit with his plains. So to answer that, if it was receding rapidly, well, first of all, when floods recede and they move out, they're not going to form what we see. There's plenty of videos online of people building physical models of this. You're not going to establish streams right away. You're not going to do any of that stuff. This is not how floods work at all. They don't shear off pure plains, and then when they retreat, form nice valleys that don't have any deposits in them, and carve out nice mountains, leave Devil's Tower behind. This isn't what floods do. All right. And as that flood retreated, by the way, if Devil's Tower was still there, you'd have a lag of deposits right in front of it telling you which way the flood retreated. And we don't have that, because things like that the flood just somehow doesn't knock over would do that. It's just like, if you have a lot of flowing water in a river and you stick a stick in there, you're going to see a little bit of deposits downstream form around that stick. Okay. So it's the same thing as a Devil's Tower is your stick, and those deposits don't exist. And they never did, because we would still, it's only been 4,500 years.
Right.
And uniformitarianism somehow managed to take hold since then, but not during the flood. We would see remnants of the big boulders, and we don't.
Let's add plate tectonics into it, because they've also got the continents moving at, I can't remember if he said 50 or 100 miles an hour. So if the continents are moving at 50 miles an hour at the same time while the floodwaters are receding, would that have an effect on it?
Will have effect on the planet. I don't know about his mythical flood, but we're back to the heat problem again.
Right. But I'm thinking, would that affect sediments being able to fill in rifts.
Rifts? Do you mean tectonic rifts, spreading centers?
Well, that's the thing. There's gonna be 2 different kinds of rifts here because if the fountains of the deep opened up these rifts where water came pouring from the mantle onto the surface of the earth, that's gonna leave some kind of a rift behind. And then in addition to those rifts, you're also gonna have the rifts from the continental movement. And because we do not see the mantle today anywhere on from the surface of the earth, these
Well,
rifts
you
had
actually,
to. Oh, we do?
yeah, I can talk
Volcanoes.
about those. In subduction zones, we have things
Okay.
called ophiolites, and there's actually one I study in Wisconsin that's Precambrian. The middle of Wisconsin used to be the edge of a continent, and
Mm,
subduction going on, and it has to do with detaching. But instead of, you get subduction and then a block. To us, it looks real big, but to the relative size of the plates, it's not. It'll buckle off, and as that
mhm,
subduction occurs, it just gets attached to the land, and it just, as that closes, it gets moved up with everything else, and eventually it's on the surface. I think that was pretty accurate. So we do have sections of the mantle, but it's just the lithosphere. And usually in ophiolites, we may not even get to the mantle. A lot of ophiolites just get down through the crust. Um, but that's the exception. As what you're calling about for rifts, I've heard young Earth creationists say the Mid-Atlantic Rift is where it happened. The water came from there,
mm,
but no evidence, nothing like that. And I think young Earth, the way he's talking, the way he talked about movements, Wegener and continental drift is actually a rejected hypothesis. It's not. It was never theory level because he provided no real mechanisms. He
mhm,
came close. He came this close, but he didn't do it. I mean, yeah, he's the father pioneer, but pioneers aren't perfect. They're trying to figure stuff out. They get stuff wrong. One of the models was that the oceans were sloshing about and that the continents slid upon the ocean crust. Well, the continents are in the plates. They're part of the plates. They're not sliding on the ocean crust. That's not a thing. They're in the plates. So as you're shifting these continents around, you've got to subduct at warp speed, and you've got to create new ocean at warp speed.
mm,
So because that's how plate tectonics works. So that continent's not sliding on the ocean floor. It's part of that plate. It's
mhm,
moving with the plate. The continents just don't get subducted.
mm.
That's the only difference. But they're physically part of the plate. And that's where that's where Wegener failed, because he didn't know that. There's no way for him to know that. He didn't
Mm.
have maps of the ocean floor like we do today.
Sea level. So there's 38,000 feet of sediments in the Hanna Basin because there's a lot of iron oxide within the limestone conglomerate. Also, we find the same conglomerate down in the valleys. So how do we explain this? I think this gives us a big clue on what happened late in the flood, because you didn't really put a fence around where the Sphinx is right now and then just dump 3,000 feet of conglomerate somehow. No, it had to be laterally extensive. And when you connect the Sphinx with other mountains in here, it looks like we had 3,000 to 5,000 feet of limestone conglomerate that was maybe 60 miles wide north-south and maybe 30 miles east-west. And it's the same type of limestone we find in the mountaintops of these mountains. But it couldn't have come from there because it's sitting on top. So where did it come from? Here's what I think happened. I think the limestone came from the west. And to the west of us is a granite outcrop called the Idaho batholith over a wide area. And this limestone probably was continuous into Idaho. And the granite uplifted in the floodwaters, and the floodwaters moving at high speeds tore up the limestone and moved it east and formed a huge flood fan. 3,000 to 5,000 feet thick, up to 5,000, because one of these limestone mountains is 5,000 feet thick of a conglomerate.
Oh my God. Number one, I know young Earth creationists misrepresent stratigraphy to the nth degree. They'll tell you that all the sand in the Grand Canyon is across
Mhm,
the continent of North America, but
mhm,
it's not all at the same stratigraphic horizon. So the sandstone, some sand was during the Cambrian, Ordovician, later and later and later, interjected with what we see to be normal transgressive regressive deposits, limestones, shales, stuff like this. So they misrepresent the geology all the time. So I'm going to call liar, liar, pants on fire when he's saying 5,000, because I don't know the geology. Now, is there a conglomerate that's probably really thick like that? Probably not that thick.
Okay.
I mean, somebody could, what did he say the name was?
And to the west of us is a granite outcrop called the Idaho batholith.
The Sphinx conglomerate is a real thing. So he's kind of misrepresenting the fans. It's a series of fans. See, in lithostratigraphy, when we make geologic maps, that's what we use. They have to, in order for a unit to be continuous, it can be broken up physically, as long as, it appears somewhere else. We call these lenses. You can call them, alluvial fans, stuff like that. As long as it's lithologically similar and stratigraphically equivalent, you can give it the same name as a formation. Then you could break out like each of the fans and members if you wanted, or something like that. So this is not a continuous sheet. Okay.
Okay.
The laramide thrust, which this is referring to, which is one of those low angle thrusts. Well, as it comes up, this is going to start eroding, because remember, erosion doesn't stop because we get a thrust. It is eroded the conglomerate as this thrusted up. And according to this, at its thickest, apparently deposition started about 75 million years ago, and at about 56. So it was happening during the Cretaceous. The Sphinx consists more of 1,000 or 3,300 meters or 3,300 feet. Being alluvial fan deposits, that doesn't mean that's the whole thickness. It's not one continuous sheet. It's going to be broke up into alluvial fans that can come together and look like they're one sheet. Matter of fact, this happened in this exact same scenario, except in a rift, a failed rift, but a formation of a conglomerate. It's one of the rocks I study, and I redefined this unit, the Copper Harbor conglomerate, up in the Upper Peninsula of Michigan. And the Copper Harbor conglomerate, basically the rift failed, subsidence began, and the highlands started eroding. Now they're going to drop these alluvial fans, and they're going to keep moving and migrating, just like river channels will on them, and they're going to overlap. I mean, I'm actually at my job site. There's alluvial fans forming due to the fact we don't have topsoil and vegetation on this one part, and you can see the process happening. So it may be that thick, but that doesn't mean one fan is that thick. And this happens in younger or older conglomerates within the mid-continent rift as well. You'll see fan upon fan. And the Copper Harbor conglomerate is really, really, really thick. I forget how thick it is. It's thicker than this in the thickest places. And we don't know how thick it is in the middle of Lake Superior, although it probably does peter out or come close to it. But it does go up on Isle Royale. So we know it is a series of alluvial fans. And that does happen relatively quickly. I think, even though, I can't calculate sedimentary rate of the Copper Harbor conglomerate, we have enough detrital zircons from, fortunately, all this stuff is interbedded with volcanics. So we can get good ages. I think 9 million years. But that's because you had rapid basin subsidence and a failed rift. Here you got thrusting going on. You can think of a thrust fault as a mini convergent boundary, except nothing's being returned to the mantle. It's just thin-skinned, and this moves up on top. And like I said, erosion's going to continue, and it's going to stop, and that erosion's just going to peel back, and you're going to get a series of alluvial fans, like this, like this, like this. You don't need a flash flood to do that. And plus, a flash flood isn't going to need, see pictures of this. There's nice rounded, not all of them, but nice rounded cobbles and, pebbles. And that indicates they were transported, not necessarily from a far distance. When we talk about transport of a particle, we're talking about net transport. So if I say something has been transported 10 kilometers, I don't mean from point A to point B. What I could mean is there was a sea right here and the sea cliff, and it fell down 1 kilometer, came back up due to the waves 2 kilometers. 3 kilometers. That's what I mean. It's a net thing. It's not this traveled that far necessarily, although it can be. So in order to round this, you need something other than a flash flood. Flash floods do not leave rounded boulders and cobbles behind unless they were already there in the deposit that got ripped apart. They don't do that. That's not something they do. Okay. We would have all kinds of jagged stuff, and not to mention we have trees and huts and all this other stuff between there that isn't there. So yeah, the big alluvial fans aren't a surprise.
What is the big picture that went on here? Well, it was late in the flood when the mountains were rising and the valley sinking down.
The valleys of the earth go up and down, up and down, up and down. The valleys of the earth go up and down. Noah's going to drown.
And the floodwaters were eroding the tops of the mountains that were rising, starting from the west and moving east, forming this fan. Powerful evidence of the deposition from this erosion, and then the tearing it apart. Just tremendous tectonics. Probably 10, 20,000 feet of tectonics occurred here of mountains.
How much force would be needed to do this, and where would that force come from? Now, I know this is entirely speculation, but
Well, from his point of view, the flood did all this.
right.
And its vertical movement seems to be the only thing he understands. But during these thrust faults and mountain building event, it was because we started overriding not the Pacific plate. They're actually plate remnants now. We're actually starting to subduct a rift under North America. Yes, you can subduct a rift. It's weird, but it happens. And that's why the basin range is there. And it might end up splitting North America. It depends on, it's called the East Pacific Rise. You had this mountain building event, the subduction starting, and it just has to do with mountains. We can calculate these forces too. People have done that, and they're not big. When you apply a lot of stress slowly, you're going to plastically deform things. They're going to want to, slowly over long periods of time, you get elastic and plastic deformation.
Like you explained in the last video with the piece of paper and the rock.
Yes, exactly. Yes. When you apply a lot really fast, you get brittle failure on solid rock. And there is examples of brittle failure there, but his flood model, as fast as this had to happen, would not have left any ductile deformation. Nothing would have been in the elastic and plastic zone. We would have rise very quickly to that. Boom, straight to brittle. We'd have chunks of stuff everywhere. There would be no evidence of plastic deformation but there is. It's everywhere. It's all over the place. We have anticlines, inclines, basins, all this stuff in that area. But the amount of force, here's an example. I'm just going to use this example as of what happens slowly as to quickly. If I have an iron rod and say I have a vat of silly putty, which behaves usually plastically, but you can get it to behave brittly if you pull it apart faster. You pull it apart slow. I have a video doing this. It moves, but and it snaps. It's a solid. Technically, from a geologic tectonic standpoint, that's a solid. And that's probably the nature of the mantle. But the mantle's probably a little more solid than that. It's not as gooey. It doesn't flow as easily as that. But that's just an example. But if I have a tub of that in a metal rod and I put a metal rod on top of it and I can get that metal rod in there. Not a lot of force, but over time, and eventually it gets harder and harder. So I have to stop, which he's saying stop. Okay. What happens if I try to fire that thing out of a gun as fast as I can? Is it going to go through? Probably not. It might go in a little bit, but that rod, let's say the rod's made of instead of metal, because metal is malleable. Let's just say it's made of quartz. It's going to shatter. And you're not going to get very deep into that silly putty. You're applying a lot of force really fast. I mean, this is obvious. I'm going to use the same amount of pressure here and force over time, but I'm going to initiate that slowly. And I do this. Okay. So I'm slow. The only thing I'm going to change here is my rate of speed. And I can do this right all day. I can do this till cows come home. And, it's just going to, move on my hands. Now, what happens if I do that really fast?
You get a lot of
I
friction.
generate what?
Heat.
Exactly. Even though I'm not applying any more pressure, I'm just doing it really, really fast. And that energy has to go somewhere because you're using more energy. You're not creating more energy, but you're using more energy in a lot smaller period of time. Time is a huge factor in physics. It really is. So something's got to happen. That heat can't dissipate as quickly as it can here. So it's just going to transfer as fast as it can into both hands.
You just said something that I think is important, and that is you can't create energy.
Yes.
And if all of these forces are happening at once, that we're having the floods come up and the plates moving and the water's moving and all of this going on, is there enough energy in the world to do all of these things at the same time?
No, not without ripping the planet apart. You would
Okay.
have to have miracle forces to cancel out those forces to avoid the heat problem that they don't exist. There's no such thing as negative heat, cold is only, and temperature is only a measure of how much heat you have. And you can't go below absolute zero. So, so that doesn't, you need a miracle force, miracle physics. But yeah, there's not enough stuff on the earth. There's nothing that can drive this scientific way. I mean, from testable stuff. There's nothing on this planet that can drive it. Not since the days of its creation. And when that happened, something really big hit the planet.
What causes plate tectonics to move?
There's three mechanisms. Oh, sorry.
Okay.
Do it the German way. There's three. Okay. It's three mechanisms. One is called slab pull. One is called ridge push. And one is just flipped myself off. One is mantle convection. Now you look at all these cool things on like National Geographic, and they show the mantle churning, and that's the driving force of plate tectonics. There is no single driving force, but there is a dominant force, and it ain't mantle convection. Because remember, mantle's a solid, and it is a rough analogy is a boiling pot. You can use that. But what do you get? You get lots of little convection cells, and they move, right? Well, the plates are large, and they'll move over convection cells going the opposite way. So that right there tells you mantle convection is not the driving force, because we have a ton of small plates. We don't. We have big ones. And the dominant force was hypothesized back in the 70s, and everyone's like, yeah, right, dude, whatever. And it's slab pull. It's probably slab pull. And ridge push isn't strong enough. We've known that wasn't, but it will move the plates, but it's not strong because the magma chamber, the magma at the middle of a ridge does not go very deep. It's very shallow because it was created by a release of pressure and introduction of water. So it doesn't go very deep. And when I say doesn't go very deep, I mean, 50, 100 kilometers, that's not very deep compared to the earth. Slab pull, and it kind of makes sense because the plates are rigid compared mechanically. Yes, you can get ductile deformation in the crust and in the lithosphere. I get that. But mechanically, as a planet as a whole, this is rigid. And this is something you need. You need a rigid lithosphere, which is that top part of the mantle and the crust together, because mechanically, all that in the ocean will get subducted. And they're under the continents too. It just doesn't get subducted. That lithosphere has to be rigid relative to the rest of the planet. Okay. Sometimes they're the same thing, sometimes they're not. So, how subduction probably begins, and this is why the Atlantic Ocean will probably close. It will not keep growing. It will eventually close, is because of something called a Wilson cycle. You get a rift, continents rift apart, and then eventually subduction begins at the end of those passive margins, and you get compression and you get subduction. Okay, that's why we have a passive margin sequence preserved, the Huronian supergroup in Ontario and in Upper Peninsula of Michigan, because that ocean basin began to close again. Even though it started as a passive margin, it eventually became a convergent margin. So the Atlantic will probably close. It's not going to get bigger forever. The slab pull basically works like this. You get old ocean crust, okay, and it gets denser and less buoyant. and we know there's faults on the ocean floor. Matter of fact, the Pacific plate's probably trying to break apart right now. It's just too damn big. On a spherical planet, it's not stable over long periods of time. And it is moving. It did originally probably wasn't when Pangea broke up, so it could survive a lot longer, but now it's moving. So it looks like there's signs of it breaking up. But anyway, I digress. So it gets, less buoyant, and eventually you're going to get faulting. And if conditions are right, and this fault continues, which they do, it's going to start to subduct into the mantle. And it's going to bring that water down with it and that lighter rock, and it's going to speed up. And when I say speed up, I'm talking to 1 centimeter a year. I'm not talking warp speed here.
Not 100 miles an hour.
Yeah. And that subduction will pull the whole plate along because it's rigid. Well, it's not going to want to, eventually that pull is going to stop. It's not going to be able to pull probably the whole thing. So what's going to happen? You're going to get a rift form on a continent or in the ocean somewhere. And that big plate's going to split and you're going to get your rift forming. And then you get your ridge push, and that'll establish a new pattern of mantle convection. And I mean, we can see these slabs in the subsurface through seismology. We know they're there. We can see them. We're just not sure exactly how far they go into the mantle, because the mantle's plastic and eventually they become part of the mantle and they go up. We know it's at least 700 kilometers. We know that for sure. It's probably a lot deeper than that. Some may even go almost to the core. We just don't know for sure. So yeah, that's how that happens. And it's a really weird way for a planet to lose its internal heat. It's so bizarre. And as far as we know, it's the only planet that does this. We don't know why. It could have to do with this mass of Earth. It could have to do with the fact Earth has a large moon compared to itself and the mass. I mean, our planet may be the right size for plate tectonics to start on a planet. It's the largest terrestrial body in our solar system is Earth. We have nothing bigger to compare it to. If that is, what happened, because in the early days of Earth, there was no plate tectonics as we know it today. And there was probably no.
Really?
Yes. That's a whole thing. And it's one of the biggest questions of the 21st century. And he asked the old timers, and they're like, oh yeah, plate tectonics always goes back. But there's plenty of papers out there that show it couldn't have. And you look at the deposits back then, the rocks, and they're completely different in structure than modern rocks. And so the old timers, that grew up with this revolutionary plate tectonic theory, just like to extrapolate it everywhere in space and time, but it likely didn't. There was likely something else going on. And so Earth might be right at that size. We need tectonics to happen. And water probably plays a major role in it as well.
Valleys sinking. So this is powerful evidence of what happened in the retreating stage of the flood, when the mountains and the continents were rising up out of the floodwaters, and the valleys, like this valley here, and the ocean basins were sinking, and the water was running off at high speed, eroding the continents, in some cases eroding and spreading the gravel just to the east of where it was eroded from, forming this fan. And then it's interesting that there's lots of quartzite conglomerate and gravel all through this area. Some of it's high up in the mountains and some of it's down in the valleys. But the quartzite is not mixed in with the limestone except very locally, and the limestone conglomerate came first. It's kind of interesting that the belt formation probably had limestone on it, and once it got eroded and spread, then the quartzite eroded on top of it and was generally separated from the limestone. And if any limestone was mixed in with the quartzites coming from the west, the powerful turbulence probably would pulverize it, so you generally have just limestone gravels and.
Okay, did the quartzite in fact come from the west? Is that portion accurate?
I don't know. It's possible.
Okay.
But there's a couple ways this could happen. And in massive flood deposits, you don't get this kind of differentiation of sediments. We know this.
Okay.
Okay. And plus, quartzite's a lot harder, more durable than limestone is. So it would have been the first to come down in his flood retreating because it would have had more energy. It wouldn't have been less. Anyway, the quartzite could be glacial.
Okay.
All right. That's one possibility. So obviously it's younger. It's on top. Obviously. Another thing is, according to what we think and the source, this stopped. These alluvial deposits stopped. What was that? 56 million years ago. Why? Because something else stopped that was generating it, that thrusting movement. So, and what happened is it stopped, and then these alluvial fans get deposited, and it erodes back far enough to where there's no more source. So what happens after a while, you get new streams established, you get re-uplift or something like that, and quartzite will get deposited on top of it. But my money is it's on glacial. But there's numerous ways that can do this, and a giant flood doesn't address any of it. It's not a thing. You can't explain the geology from a massive flood, and they're doing what they love to do. They're taking one location and trying to extrapolate it globally. That's you don't do that. You don't do that. The Earth is a complex system. It always has been. You get some things, even plate tectonics isn't global. Believe it or not, it's not global because we have things like hotspots. Okay. So we still have some other processes, not fighting plate tectonics, but working in conjunction with it. So nothing is global except maybe our atmosphere. That seems to be global. But yeah, and even that's different in places. So.
During the erosion of the continents, when we examine the character of the erosion, we can determine that.
Okay, that quartzite conglomerate there, glacial outwash, what we call tertiary deposits or later deposits. I don't know if they're directly on top of the Sphinx or not. He doesn't. But it very well could be because the Sphinx is older, but the thing is, that's only if it's sourced from somewhere else. But we have a lot of these tertiary gravels in play. When we mapped these for field camp, that's what we called them. They looked a lot like that. And their origin, couldn't have been glacial because they're tertiary. But you'd have streams becoming established in places. And streams and rivers are not long-lived things. They are not. Most streams and rivers have a lifespan of tens of thousands of years. So that's it. You get exceptions, yes, I know, like the Mississippi, but the Mississippi's not as old as the oceans.
First of all, that it was rapid and recent. For instance, along southern Africa for about 2,000 miles, the edge of it is ringed by an escarpment. Escarpment is a high cliff. The escarpment is sometimes vertical, sometimes sloped like this. It looks like it's flat on the top, like a tableland, as they call it, but it's really a planation surface where it's been planed flat during the sheet flow phase of the flood. And then you got to have the escarpment, and then you have a coastal plain. Now there's debate among uniformitarians on the origin of these escarpments. In fact, they have serious trouble explaining them, but it looks like the sediments were close.
I guarantee you, if you look this up, you're not going to see we argue about this. This is just their standard stuff they spew to get that. Ooh, they can't figure it out. Thus far, God did it.
Yeah.
And we don't. And I'm not familiar with geology of South Africa at all. I'm familiar with what we call the Kapval craton because that's Precambrian. But this stuff, I'm not. My guess is it's just a normal fault area, series of normal faults. And you had coastal plain deposits. Younger creationists say that all the time. Uniformitarianists, which isn't a word anyone uses except young Earth creationists, just like evolutionists.
Yeah.
The second you say those things, we know exactly where you're getting your information from. And there's some people that only use those words, so we can probably pinpoint the person. Whenever younger creationists say uniformitarianists can't decide, it's a big problem, it probably isn't. They're just trying to get you to say, oh yeah, that must be a problem, so yeah, I'm just going to ignore that, when it's not a problem.
Closer to the coast, the sedimentary rocks, mostly, there's sometimes igneous rocks in them, and that the escarpment backed up from the coast, sometimes maybe 60 miles or more. It appears that the water from the flood was flowing off as a sheet perpendicular off the coast towards the ocean. And it was forming like a huge waterfall, or in this case it'd be kind of a little ripple, because we're talking about deep water. And so it's eroding the escarpment back. And then the coastal plain, it shows some dissected planation surface.
Questions I had. If all of Africa was a single plane and the water is creating channels, how is it falling? Where is the lower area for the water to fall to? Is the first question.
Yeah, if it's, well, you remember these all lifted up, it
Mhm.
cleared off in the flood. Then the continents were all exactly lifted up at the same rate everywhere. And what would happen in that kind of unrealistic scenario is if you had rain, but see, the water's already gone off there.
Mhm.
So this anything left would have to be due to rain and the establishment of streams. And what happens is on escarpments, you do get rivers and stuff, and eventually that pulls back. You know,
Mhm.
the sea comes in and erodes it too, creating, this isn't a mystery. No, nobody argues this. Okay, we can go observe it. I can show you a Precambrian escarpment and Baraboo. Model is a very generic 101 type scenario.
Okay.
And the younger creationists do this a lot. They use a lot of 101 concepts. And 101 concepts by nature are very simplistic, textbook scenarios, because it's there to teach you the beginning stages of something. I
Mhm.
can't teach you how to use a stereo net in structural geology until you understand how rocks form.
Mhm.
Okay,
Mhm.
so I can't just push you into that. You're not going to succeed. So yeah, I mean, you got to start somewhere. Crawling before you run. You know,
Mhm.
and that's why higher education, I believe, is very important. A lot of people dog it. Oh, my experience. No, your experience can't necessarily. Your experience, if you're academically proficient, you can look stuff up like lay people can be scientists. That's perfectly fine. I have no
Right.
problem with that. But the point of a university is to take you through those steps quickly. So you do it in 4 years instead of 34 years. And there's some stuff you may never learn through experience. Like, who would think you can model planar surfaces on a stereo net, which is basically a bowl? I mean, that's
Mm.
counterintuitive to logic, but it works. And I've demonstrated in videos the whole concept behind it and how it works. And yeah, so, experience has its limitations. Now, especially if you're not academically proficient in scientific thinking, you might think, oh, I can't solve this problem. You're going to walk away from it.
Mhm.
A layperson who is academically proficient would be like, oh, I should look that up. Maybe I
Mhm.
figure this out. And that's great. And I wish there were more people like that. You don't need college to do this, but it does help. Unlike Meteor Man here. Can I just call him Meteor Man?
How did some of the land get lower? That's entirely a speculative question. I'm not totally asking you that because, obviously this is his speculation, not ours. But do you know what he's been talking about how the plate tectonics and it would cause some areas to lift. I guess it would cause some areas to go lower then too, wouldn't it?
Yeah, his concept of plate tectonics is more something like we call lid tectonics. And that's not something that happens on Earth. And,
Mm,
and even if it did, we wouldn't have low angle thrust faults or detachment blocks. We would just have series of high angle, normal, and reverse faults. That's what we'd have. And they'd be delineable and you'd be able to see them. So, and the planet would probably be plated more like a soccer ball.
mm,
You would have some plates rising up and some sinking down. That's
mhm.
trying to balance that out. But that's not what we have. And it doesn't explain any of it. It's trying to confuse you. Because
Mhm.
and talking to you makes I'm so glad because you catch things I won't because I understand the process and I'm just like, that's stupid, and I skip it. But you don't and I may not understand you don't understand that. So you stop me and we can talk about it.
This came from one of the comments from one of the viewers on part 1, and
Yeah.
it's an excellent point. Why are the Tigris and Euphrates rivers still there? And I'm not really expecting you to answer that question because the obvious answer is if his flood model were true, they wouldn't be. But the Bible describes where the Tigris and Euphrates rivers are
Mhm.
in Genesis before the flood, and after the flood, they're still in the same
They
place.
wouldn't be. That
Right.
comment or a great point. They wouldn't be there.
Yeah,
because
yeah.
you can't shear off everything and then reestablish exactly the same stream pattern. That doesn't happen. I mean, that was a great point.
Yeah,
Great.
it was, it was. I
You
don't
can say the
remember
same
who
thing
ma
about any major river, but that I get those two because, like you said, they were described before the flood. You know what rivers weren't described before the flood? The
Hmm,
Mississippi, the Amazon, all those other ones which they didn't know about. And that's another thing too. You got all this tectonic movement and earthquakes and stuff. Why was no? They mentioned fountains of the deep, so they supposedly know about water coming from the ground, but they don't notice massive earthquakes and continents shifting. I, that doesn't make sense. See, this young earth creationists, everything they have is extrapolation, and it is starting at the. People say this all the time. It's true. They start at the conclusion and they backpedal and they use argumentation instead of evidence to make their point. They're not doing science, and then they get Meteor Man instead of a professional geologist, structural geologist, whatever, because he doesn't know either. I guarantee you, he doesn't know.
they have one geologist that is a young earth creationist, don't they? I can't remember
Oh,
his
they have
name.
several.
Okay.
Baumgartner, Austin, Austin was actually, I believe he's a cold jet. And then you have others that aren't kind of so sure, but
Mhm.
they don't like, I did my critique of, is Genesis, whatever science, whatever it is. And I got the one guy and he's talking about the coquina sandstone and he's not a geologist, he's actually a biologist. And
Mhm.
there's some things in the field he did that kind of gave me twitch eye, but he's not a structural geologist. I get it. And there's nothing really wrong with the way he did things. It's just not as accurate as it could be. And not once does he say the Great Flood in that entire thing, nor does he talk about a young Earth. He talks about the coquina sandstone and how it formed. The coquina doesn't go to the core of the Earth to top Mount Everest. So you can't extrapolate even at that. We think it. The problem with that is there was some controversy about whether that was windblown deposits, aeolian, or shallow marine. But that doesn't mean there was a global flood. And quite honestly, in the grand scheme of things, it probably doesn't matter.
The fact that you still have cliffs and steep slopes indicates that these escarpments were eroded not very long ago, because vertical faces.
Okay, I just had the comment in here that I cut his description of various escarpments. Can you speak to the cliffs being evidence of the escarpments developing recently?
Well, it looks to me like, has he moved back to the Grand Canyon in Western US? Because it looks like he's moved back there.
Yeah, he has.
Technically, an escarpment's just, lowland, highland with a nearly vertical cliff or close to it. It doesn't have to be vertical. But if you're in the area of the Grand Canyon, you have that slow uplift. It depends on what you mean by quickly. Did those
Mm.
escarpments form quickly compared to the planet's age? Yeah, they did. But it didn't happen 4,500 years ago or 3,000 or 2,000. That's not a time frame that this can happen in. And as we've discussed, the Colorado Plateau has been lifted up and it's also tilted the grand staircase. The one time you showed a cross section, you saw that. You saw it was kind of like this as you went this way. The deposits are deposited relatively level and flat lying. Deformation happens, tectonics. By the way, the third guy's Snelling. I can't believe
Oh,
I got
yeah.
his way. So escarpments, it's a relative thing. And one mystery that actually is a mystery is exactly how the Grand Canyon took on its modern shape. But we're coming back to an old idea. We do this a lot in geology. I don't know why this is. As the Colorado Plateau, I personally am on the side of it being older than very recent. The fact that it's a meandering river that cuts through it, and we know the Colorado Plateau is rising up at about the same rate erosion's eroding it down, should be a big friggin' hint. A long, long time ago in the 19th century, it was postulated that that there was an established river. The land rose up. Well, as that rises, that rivers no longer has a baseline. And only highly meandering rivers form from lateral cutting. But this is down cutting again. So as this land became lifted up, it no longer had a baseline. So it starts down cutting and it keeps the meanders. because it's not happening fast enough to tear those meanders apart. That talks about a mantle situation under the Colorado Plateau, and the reason why we don't have volcanoes and rifting going on there. And, so we come back to these old ideas, and I always thought it took, longer than 20, 30,000 years for it to form.
Mm-hmm.
But, probably in the order of 5-6 million, maybe a little more than that.
And also, uniformitarians have the bind where these escarpments are fairly young. They're in the Cenozoic era, probably around 50 million to 30 million years ago in their time scale. So they're recent. In fact, the erosion is too fast.
Okay. Are you searching for a mechanism to explain this time scale, Stephen?
I don't need to search.
Because that's what he says, that you're searching for this.
No. 50 million years is more than enough time to create a landscape like that. You know what isn't? 1 year. No matter how much water you throw at it. This is just, it's just that creating another, we're searching, we're looking. They don't know when we completely understand it. And like I said, with the formation of Grand Canyon, its modern appearance, there is some, but we're testing it. We're doing what scientists do, And matter of fact, the pullback hypothesis that happened quickly from the drainage of Playa Lakes up above, that was a big thing. You saw a lot of specials for a couple of years, but that has been falsified. So we go back, that's what we do, And as for those basic escarpments, all you need is slow uplift and the establishment of streams. You don't need anything magical to do this. Nobody's looking for anything. And you know what? 50 million years is more than enough time to do that. As a matter of fact, that's slow. So the uplift hasn't been drastic.
The valleys of the earth go up and down, up and down, up and down. The valleys of the earth go up and down. Noah's going to drown.
There's places that uplift very quickly, in a matter of a couple million years, or subside quickly, like the Copper Harbor conglomerate forming in 9 million years. 50 million years is more than enough time. That's just it. Okay, I think it's on my piece.
Their time scale, so they're kind of searching around for other mechanisms, but during the flood, they can form rapidly. And the fact that there's still vertical cliffs and steep slopes indicates that these escarpments were formed not that long ago. And since there are hard rocks at the top of the Pumpkin Buttes, you can add probably another 1,000 feet, indicating 2,000 feet over the whole Powder River Basin.
Okay, if this was all a level plain at the beginning of the receding stage and is now 2,000 feet higher now than it was then, where did all the earth go?
In his flood model?
Yeah.
Magic. The explanation would be it got dumped downstream into the Gulf of Mexico or Baja, Gulf of California, over there somewhere, or off the western coast of the United States, which we know it hasn't, because I don't know, there's these things called mountains in the way, and that's a great point. If his plane is was the top of those things, why is it so much further now? The waters receded, and receding waters don't do that. They don't pull the earth with them. That's how they function. All right, they erode. So that was a very good question, and I know he doesn't have an answer for it. If he did, he put a testable model up here, and he doesn't do that at all, ever. I may be talking to and trying to debunk him, but I've got mountains, if I understand it correctly. There's some areas I don't understand very well. I'm coming from a place of a lot of scientists that came before me who literally have my back, and you can go look it up right now. That's the difference between me and them. A lot of people say, you're just talking too. Yeah, but I've got all this stuff behind me. You guys have the Bible.
Yeah.
That's all. And then you try to make the square peg fit into the round hole. That's all you have. And if you had real science, you would be putting up your testable models. And they don't ever do that. Or they'll show you a model and they won't show you the maths behind it because it doesn't work. That's why, and yeah, I mean, like I said before, I can model a stop sign growing out of the ground using bad math. But does that mean it happened? No, because we don't observe stop signs growing out of the ground. Are stop signs, is that a uniformitarian idea too? I mean, come on, dude. Put forth something I can test, or you have nothing.
Around the Grand Canyon area, where you've taken off anywhere from 6,000 to 10,000 feet of sedimentary rocks in the whole Grand Canyon.
You're not going to form a Grand Canyon as an outwash channel for a massive flood. You don't get that type of looking of the landscape. I've already given how I think the Grand Canyon formed. And, I actually did a video a long time ago, I think, where when I bought my house, I had a pool in the back, above ground pool. So I had to murder it because I hate those things. And in the early aughts, those were so common around here. So I got rid of it, and below was sand. So I'm like, oh, I had the opportunity to model some quick flooding. So that's what I did. And you know what I never got, no matter what I did? A Grand Canyon type deposit or erosion feature. It can't carve something like that. We know that through modeling.
If everything, if the whole surface of the earth was 2,000 or 20,000 feet higher at the end of the flood, to get 20 feet of water on top of that, because the earth is a sphere, the amount of water that you're going to need in order to flood the whole earth has now become vastly greater. One of the points that AIG makes is, the Himalaya mountains were much smaller back at the time of the flood. That way we can have 20 feet of water that covers even the mountains. But if he's making the point that everything was 2,000 feet higher, you now need 2,000 feet more of water to cover the whole earth.
Yeah. And the earth is a three-dimensional object. And a sphere is the most efficient way to pack matter into something. So if you raise sea level by 20 feet, you're not just adding 20 feet of water. You're adding an entire, probably close, I don't want to speculate, but you don't have to raise sea level 7 kilometers to get all the water on the earth. Because the earth is a sphere, it spreads out. That's why if the poles melted, we wouldn't be, the whole planet supposedly got flooded because the ice caps melted. It's not possible. It's not enough water. There may be a Pacific Ocean full, there's not, but just say hypothetically, even if there was a Pacific Ocean full of water in those ice caps and they melted, we're not going to get a doubling depth of the water. It's a fraction of that. So yeah, the earth is a sphere, people. It's not a circle. It's not a line. Younger creationists are like flat earthers. They have a real time working in 3D.
Rounded rocks, which many of them are quartzites from 300 or 350 miles away.
Is that true? Are the rocks in the Grand Canyon from central Idaho?
I don't know, probably not.
Okay.
But we had catastrophic outwash of Missoula, Lake Missoula. There are channels that went that way, went south a little bit, because obviously it couldn't, go strictly west because we had the mountains in the way. So it had to go somewhere. So it's going to go downstream. So it's possible. But if there are quartzites on there, it could have been sourced from a more close, because the younger creationists never talk about the Grand Canyon supergroup. The Grand Canyon supergroup are the Precambrian metasedimentary rocks that are 3 times thicker in the Grand Canyon than the entire Phanerozoic sequence. It's just they've been faulted in and out because of tectonics. And there's quartzites in there. Quartzite isn't quartzite everywhere on the world. Quartzites occupy different stratigraphic horizons, have different characteristics. It's very rare to be able to sit there and say, oh, this quartzite in Idaho must be the same in the Grand Canyon because they're both quartzite. No, you've got to demonstrate that. And you can get quartzites forming many different ways. So that any quartzite in the Grand Canyon could be from the Grand Canyon supergroup. For all I know, he doesn't say because he doesn't know. I guarantee you the entire concept of stratigraphy, sedimentology, and structural geology is beyond him. That's why he became a meteorologist.
The Beartooth Mountains represents one huge planation surface.
No, that's going to say no to that.
Okay.
Because that's just I mean, I can discard that because he doesn't back it with anything. So I'm just not going to address every little thing.
It's been dissected. Probably when it came up, it cracked, and water during the channelized flow phase of the flood took advantage of those cracks. And
Okay, so a plane uplifted from tectonic movement, water drops into the cracks instantly, geologically speaking, forming canyons in the rock. Is that possible?
Sounds like what he's talking about is joints and fractures forming in rock, and these are natural things that will form in rock, and
Okay.
streams will follow them. It's a specific stream type of stream pattern that develops in these, but not most of them. He says cracks. He probably is talking about faults or I don't. He doesn't say. Saying a crack is like saying, yeah, the Earth is made of rock. Now, what's this? You know, it's them and their bedrock and cracks. Makes me wonder what they're playing with in reality.
now, this planation surface, it could have formed at 2 times during the Genesis flood. It could have formed early in the flood as an exhumed surface. The exhumed surface is one that's formed, flattened, and then sediments pile on top of it, and then it's re-eroded or exhumed. As it uplifted, there's evidence that the top of this granite was eroded because we find erosional remnants of the
Okay.
Could have.
Yeah. Is that possible? I cut out the next part where he says it also could have been runoff phase. He's already said that at least 4 times, and I didn't think we needed to do it again.
No,
But I've never heard of an exhumed surface.
you can have geology called zoom topography.
Okay.
Actually, with the Baraboo Hill, what do you call it? The Precambrian surface.
Mm-hmm.
A lot like the modern surface. Not a complete match, but we have Cambrian and Ordovician on top of the bear as well. So it's not completely this, but the Baraboo quartzite likely stood as hills in an advancing sea, as just breakwater. That's why we get conglomerate. That topography is reflected in the modern landscape. We call it exhumed topography, but it's not a perfect match by any means. But that actually is a thing, but I don't think he's not applying it that way. And
Yeah.
I think when he's saying exhumed, he just means hollowed out and something beneath was exposed, which in a layman's sense is correct use of the term. But we do have something called exhumed topography. And it's, you know, sometimes it's hard to see if he's speaking like a layman or using the technical term. It's part of the confusion. I don't know if it's an intent to confuse or they just don't know. It's probably both, but you know, so yeah, it's tough. It's tough. And that's what they're hoping. They're hoping on that.
But there's evidence that this could have happened late in the flood during runoff. The reason is because you have a lot of plain mountains in the area. The top.
Okay. I wish he would make up his mind. Earlier, he said the whole Earth was one plane at the start of the runoff, and now maybe it was, maybe it wasn't. Is this supposed to be evidence of a flood or speculation about how you could make a flood model? Do you have a flood model or not?
Pretty much. This is the kind of stuff, and I'm gonna give younger creationists a little bit of credit here. This is the kind of stuff when you go out to a virgin area where nobody knows anything and you start thinking, well, how could this have formed? But you don't just sit there and go, God did it. Take your butt up to the rocks and you start looking at the geology, you start looking at the landforms that have caused, and you start looking for relative dating, you know, what came first. You know, you're not going to get an actual date by looking in the field. You know, that's, so I don't have a problem with somebody going up and saying, was this carved by floodwaters initially? But then they take that and they use it as evidence. And it's not evidence. You haven't formed a hypothesis yet because you don't have a testable model. You're drawing a conclusion from an initial speculation. You're absolutely right about that. That's not how science works. You know, could have, should have, would have. You know, I could have been born a baboon.
And when the Wind River Mountains rose, it eroded the sedimentary rocks off the top of it, and it tilted the sedimentary rocks along the edge. And some of those sedimentary rocks that were tilted were plain flat. And that would happen late in the flood. So at this point, I have not made up my mind whether this is an exhumed planation surface early in the flood or...
And this to me is the biggest point of the whole thing. I rest my case. No flood model. If you can't interpret the evidence trying to get the result you want, why not just accept the experts that actually do this work?
But my book. And, I'm not the kind of person that goes around dogging other people's, religions. You believe whatever you want for all I care. But
Mhm,
when you start pretending it's science, then we got a problem.
mhm,
And
mhm.
you're absolutely right about that comment. And there it sounded like he might have used exhume the proper way a little. Erosion does not cause rocks to deform. That doesn't happen. You need tectonic movement for that. So that's one thing that the fact that he doesn't understand that right there shows me Meteor Man has his head in the cloud.
Yeah, to me, that's the biggest point because that destroys everything he said.
Mountains formed and erosion occurred because this is mostly underwater, and often the planation surface was totally destroyed, so you have pretty sharp mountains. Other times it wasn't. So the planation surface is still left on the tops of the mountains. And I go along with this because there's a lot of planation surfaces leaving in the Rockies. You still see some in the tops of the Colorado mountains. You see the Wind River Mountains, the Uinta Mountains are planed.
It's again not possible with the Tigris and Euphrates rivers still existing in their pre-alleged flood locations. Elevation varies from 1,200 to 170 feet. I looked it up. If the land was planed and then uplifted, rivers would move.
Yeah, was that supposed to be 1,700 or 170 feet?
170. It's
Oh, it is
170 at the lowest and 1,200 at the highest.
highest. Okay, because I make typos too. So I'm not dogging you. I just wanted to clarify.
Yeah.
Yeah, now he's putting planation surfaces. By the way, planation, I didn't say this last time. It's not an actual feature, it's a process. There's
Mm.
types of planes, okay, which he
Mhm.
is addressing. But like you said in the beginning, he's just talking about like this whole planet was just planed, and now it's not. And he's grasping for straws here. He's finding ridge lines and saying there's planation surfaces on there. Dude, you're making shit up. You just are.
So I go along with Ollier and Payne's hypothesis that we had a huge planation surface at one.
He brings up Ollier and Payne's book on the origin of mountains. I looked it up and I found this review of his book. This book will disappoint most geologists and is not to be recommended. The authors are geomorphologists who believe that the importance of geomorphology in understanding mountain building has been underappreciated by the geological community. This may be true, but this book will not help their cause. The stated theme of this book is the narrow assertion that all mountain ranges form by vertical uplift of plateaus, followed by erosion with or without gravity sliding. This book is basically anti plate tectonic, and instead of enlightening the reader, we are treated to one sided views, unsupported assertions, obsolete information, and generally sloppy scholarship. Basically, what you've been saying all
Say the
along.
whole time.
Yeah.
Yeah. You got to remember books too. Some books are peer reviewed, but
Mhm,
anyone can write a book.
mhm.
It doesn't. They're not usually they're not peer reviewed. Okay, and honestly, my guidebooks of geology that I write are not peer reviewed, but I study in those areas and I put my references in there. I tried to have Dave peer review them, and he just didn't have the time. So if you do find anything in those, let me know. But
Mhm.
they're pretty good. But in all honesty, they were not peer reviewed. Okay, nor do I claim that anymore. That whoever wrote that hit the nail on the head. The geomorphology is a reflection of the geology. It's not the other way around. I don't think we underappreciate the geomorphology, not when it comes to recent landforms like kettle lakes, moraines, stuff like that. But when you're dealing with rock units that were buried for so long and now exposed at the surface, those things become less important. That guy was right. I mean, we do it in structural geology. I ignore geomorphology usually. It's helpful in feeling like, oh, what's that over there? That looks out of place compared to the following topography. And it's a good place sometimes to draw in horizontal level units, sedimentary units, to find where formational contact is. It can be useful in that way too. And to make geologic maps if you're drawing alluvium, stream deposits, stuff like that. So it's not completely ignored, but it's not this big thing either. It's a part of the greater whole. That's why no one really studies just geomorphology. It's part of something else. And glacial geologists are also geomorphologists. They're both, because you got to do that. And geographers are usually geomorphologists too. And so are some geologists. But it's not the kind of thing you can address to extrapolate a geologic history. You just can't do that because landforms change. We know this. And some of them we can measure and observe directly, like a debris flow, an earthquake changing the landscape, the flood, the Mississippi floods of the 1990s, all this stuff. You can't just use geomorphology. That's not a thing. That guy hit the nail on the head.
They filled it up with rounded rocks. Can you imagine that? In fact, the pressure was so great on these rounded rock that quartzite against quartzite caused pressure solution marks in some of the quartzites. So once it deposited that 15,000, actually it was more, because we know the top was eroded. It was probably 20,000 feet, and then a lot of that came up too and was eroded off.
Okay, I'm getting very confused. This is supposed to be a valley, and now it's a valley that lifted up. So are the mountains and valleys going up and down? Is this a wheels on the bus kind of thing?
The valleys of the earth go up and down, up and down, up and down. The valleys of the earth go up and down. Noah's going to drown.
I honestly think that he is trying to just say that they uplifted, but these other processes happened. He may or may not consider them one single uplift, but he has to sit there and interject sounding like other uplifts to get the shit to work. It is very confusing. And to someone who knows geology like me, it's word salad. It's confusing. It confuses me because it doesn't make any sense. And I can't imagine what it's doing to a layperson,
So in reality, valleys do go up and down over millions of years, and he's trying to cram that into 1 year. Is that what's going on?
It must be, because,
Okay.
we know you're right. Valleys can be uplifted as well. And, that's all due to tectonics.
Quartzite does not outcrop in the state of Wyoming. The nearest source to the west, which is up current in a flood, is central Idaho, approximately.
Okay, is that true? He claims the water is flowing from west to east in the flood. So how did Noah's boat manage to go north and slightly west in these 50-mile-an-hour currents?
Well, and he actually said something completely false there too.
Okay.
I know this for a fact because it's related to the Huronian supergroup rocks around Lake Superior. Snowy Pass, Wyoming has a lot, and it's probably time correlative to the Huronian supergroup.
I had never thought about that until he started talking about the 50-mile-an-hour currents, that Noah ended his journey very close to where he started it.
Yeah.
How did that happen?
I have to do the magic hands thing again.
Right.
And besides that, there's about 5 or more mountain ranges between here and its source in central Idaho. So how did it get here? Did it skip over the mountains that were here? Oh no, it was spread long distance before the mountains uplifted. These quartzites have the
what's that called? Presenting a straw man? Is that the right logical fallacy?
Mm-hmm.
But he's making up a fake scenario.
Mm.
He is sitting there telling you the closest quartzite is Idaho, which is completely false. There's closer quartzites. There's quartzites in Wyoming. There's quartzites in Montana. It's just.
Well, he even talks about the Montana quartzites at one
Yeah,
point.
he does.
I skipped over it, but he talks about there being gold in some of the quartzite and how it's being moved with the gold. Yeah, it's.
He doesn't know. It's quartzite. Thus far, it came from where I said it did. It doesn't matter. You don't need to absorb any of it anyway because it's complete dribble. I mean, could have done this. Probably should have. And like I said, how did Noah's boat survive? But anyway, it really wasn't a boat, was it? Was it more like a big floating box?
Yeah. Mhm. Mhm.
It's
And somebody in Korea, I think South Korea, made a model of what Noah's boat is supposed to have looked like and subjected it to the forces that they're saying would have been the forces of the water at the time. But they don't have any rocks in their model. They're that where they tested the survivability of the boat, they didn't have any rocks moving.
Well, yeah, and they're also going further and beyond in their water pressure and stuff like that. And I mean, to move this kind of water, why are you not generating massive? What are those waves called? Rogue waves?
Mhm.
Why
Mhm.
aren't you generating these? I mean,
Well,
it,
and that yeah, that is another point, and that's a point that I make, when I talk about that, because one of their flood predictions is that there were giant tsunamis, and that's what washed over the North Atlantic continent. But to get the boat to survive, those same tsunamis that they predict could not have existed.
the floating box would have been destroyed.
Mhm.
I mean, this kind of thinking is good if you're in the early stages and nobody knows, but you've got to test it for my hypothesis. You can't just keep talking.
Mhm.
You can't argue your way into evidence, and that's exactly what he's doing.
Yeah.
Science does not go like a courtroom. That's not a thing.
Visual percussion marks on them, and also they have pressure solution marks. Now, pressure solution marks are these white marks on this quartzite cobble right here. It's rock against rock, and where they touch each other, the pressure is so hard that it kind of recrystallizes the hard quartzite right there because
An actual thing he's talking about,
Okay.
thing, but no amount of water is going to do that. Water's a liquid, you can only put so much pressure behind it.
Mm.
You don't get pressure solution rocks at the bottom of the ocean either. What you need is something massive, something heavy, like, I don't know, more rocks to do this. This is nothing, more of nothing. This is more. I have an idea in my head. Now you should be trying to run experiments on this, at least some equations. Can water even do this? And I'm 99% sure you're going to come up with the answer no. And if it
Mm.
could, it would probably shatter both of the rocks. If not one, just one. It's one rock doing, or a body of rocks against another being with some sort of tectonic force behind them and compression to get them to do that. And as for remineralization, that depends. You're not going to get that from water. And another thing too, all this water sloshing around, I thought it would dissolve some of this limestone too,
Mm.
but whatever.
find is, of course, percussion marks, semicircular cracks on one of the hardest rocks in the world. And it's pretty heavy and dense because all the pores of the sandstone have been filled in, recrystallized during the metamorphic process forming the quartzite. And then during the transport process, the extreme turbulence, I believe, caused these percussion marks on this rock.
Currents aren't going to do that. Notice he said metamorphic process,
Mhm.
which is how you get quartzite. Technically, quartzite's a metamorphic rock. And if it has conglomerate in it, which like the Baraboo does, you can get things like pressure marks upon other rocks that are adjoining because there's a mile or 1.6 kilometers of sediment put on top of it undergoing a compressive metamorphic process. You know what does not metamorphose rock? Running water. To metamorphose rock, you need heat and pressure, not just pressure. That's not going to work, okay? Because the metamorphic process, the rock needs to be heated to recrystallize. A lot of minerals only form under certain pressures and temperatures. And there's a whole, from garnets to starlights, there's a whole mineral assemblage that when we look at metamorphic rocks, we can confidently assert through experimentation the phase of metamorphism and how deeply these were buried. At least it's going to be plus or minus, a few dozen meters. Okay, we can't get down to the meter. That's not a thing. Phases go through, different mineralization. Now, quartzite's a little different. This works really well in mudstones, but quartzites are usually devoid of mud. Okay?
Mm.
Pretty much most quartzites are, metamorphosed quartz sandstones, or quartz aeronites, as we call them. Dominantly quartz. Is there other stuff in there? Sure, but no more than 2 or 3%, maybe 5. I think is the limit, 5%. So there could be other stuff in there, but you're not going to do from a bunch of water metamorphose a rock by putting another rock on top of it. That doesn't happen. I don't care how much water you got on it, and I don't care how much force you got behind it, because once again we're going to introduce the heat problem, and you're just going to melt everything and come back to one large igneous body anyway. So he's applying, and young Earth creationists do this too. He's applying a principle incorrectly.
4 out of 5 of them depend on water coming out of the nearby mountains.
Okay, this is where he's talking about the pediments. He says there's 4 theories about pediments,
Right,
and he says that 3 out of the 4 of them aren't really the ones that he wants to deal with. He wants to deal with just this one.
The thing is, those don't work because water coming out will dissect and destroy a pediment that's already there. Pediments aren't forming today. They're being destroyed. Like this canyon right here.
They are.
Yeah, a pediment is a geomorphic feature. It's just a gentle slope in front of a mountain. It doesn't tell you about the type of rock there. And the type of rock there is going to tell you how it formed. An alluvial fan was this fast running water. Is it just a pile of sand blown against the mountain due to the wind? You can get things to form, geomorphologic features to form in different ways most of the time. That's why using geomorphic features does not fit his model, because he's not addressing the exact type of rock. But pediment they're just gentle forming slopes in front of a mountain. That's all they are. And like I said, have you ever been to Great Sand Dunes?
Yes.
Yeah, isn't it great? Isn't it great? But some of that topography is pediment, and it's windblown sand, Or you can go to, and it can be broad. You can get broad alluvial fans, because as that stuff erodes and you get those cobbles and boulders, that stream energy goes from high to zero like that. So it's going to dump its load, and it's going to take it a while for that energy to disperse. So it's going to go for a while, and then it's going to slow down. But so it's going to dump its load, and you can get broad alluvial fans that way that are just low lying. But if I remember correctly, the term pediment is usually referred to as bedrock surface, low bed. If I remember correctly, but it is a general geomorphic term, so it just means shallow sloping land surface.
About 9 rivers start in the southern Tibetan plateau. Water was going perpendicular to ridges that were either coming up or the water was lowering. Remember, the water was draining off the continents as they were coming up. And as it's going perpendicular to a ridge or a mountain range, there's low spots generally, and the low spots, the water will tend to funnel through there. And as it funnels through there, it'll tend to accelerate. It's like moving water through a wide pipe into a narrow pipe. The same.
Okay. Now, my problem with this is there's a lot of rivers that flow north and south. So if all of the water is moving from west to east, why are the ridges perpendicular to the flow of the water? If the water is going east and the gaps opening are to the south, you're not going to get this effect, are you?
Eddies that are magic.
Like the Mississippi River. If all of this water is going from west to east, how is it channeling south to form the Mississippi River?
He doesn't know. Well, I guess this is as it's retreating, so I guess the landforms are getting in the way, so I guess it could go different directions. I assume that's what he's getting at, but he doesn't say that. But actually, the concept of the formation of these is like high school level. It's not, there's no mystery in how a youthful river cuts a valley. As these things uplift, erosion is happening. Some slopes become unstable. So a river system, especially where it rains a lot, is going to start to cut into this. And as this lifts more, it's going to, the valley, not the river, the valley is going to move up the mountain, cutting it down further, because this whole thing is trying to establish a baseline. And eventually you'll get 2 on a side of a mountain, which will meet, one will dominate, and then eventually that ridge will disappear. It'll go right through. Unless you've got some sort of fractures or jointing controlling this or faults. But generally, that's how there's no mystery in this, none at all. Whenever a young Earth creationist says the uniformitarianists have no idea, you know they're full of shit from that point on. Just ignore them. Because they're creating this false perception that we don't know what the hell's going on, and we completely know, and they're just making stuff up. I mean, we can measure these things for me. This isn't tough. You know, I mean, there's no mystery as usual. Do we know everything? No. There's geologic mysteries. The Grand Canyon. What kind of tectonics worked on Earth before plate tectonics? These are mysteries. These aren't the things they care about. You know, they care about stuff we've understood for 200 years and trying to make you think we don't know any basics, because that's what they do. They try to attack the basics. Attacking the more advanced stuff is easier because nobody knows about it. And that's something you could do. You could kind of attack a little bit more advanced stuff, but still it's not a falsification. So they go for the base and they make the stories up that we don't know how streams migrate. You know, this is ridiculousness. This is so ridiculous. This one seems a little more targeted, not usually at preaching at the choir like most of these videos do. This seems like it's trying to expand to a newer audience. And at least to me, it seems that way. Because he's going through a lot of stuff really quickly. So, you know, it's just there's nothing in this video that can't be explained, that we don't have a working model for or anything. That's it. And another thing, there's no such thing as secular geology. It's just geology. Just like there's no such thing as Eastern or Western medicine. If it works as medicine, it's medicine. Okay. It's just the way it is. All right. Yeah. So I hear that all the time too, and it makes my eyes roll. But I understand them using it for distinction. But that distinction only works if there is a variation. There's no young Earth creationist geology because none of it works. Soapbox down.
Okay, and I think that's a great place for us to end because this is exactly what I wanted to accomplish.
Okay.
You know, we've gone through all of his points. Did I skip sections? Yes. Did I skip anything of significance? No. If you disagree with me, find me a section that you think is of significant, leave a comment, and we'll address it, or I'll address it in a future video. But overall, I think we have accomplished our purpose here. There is no flood geology that explains the world as we see it today.
Exactly.
Thank you so much for your help, Steve. I could never have done this by myself.
Thank you very much.
Appreciate your help.
Thank you for having me. Have a nice day, everyone.
Live your life.
The valleys of the earth go up and down, up and down, up and down. The valleys of the earth go